In this video, I'd like to cover SN1 reactions. And as you'll recall from my primer video, SN1 stands for nucleophilic substitution unimolecular. And what that means is that the rate determining step in an SN1 reaction is dependent only on one molecule, not on two molecules like in an SN2 reaction. And so it's very simple to draw the mechanism. So here we have T-butyl bromide. And the first step in an SN1 reaction is simply that the leaving group leaves. And it leaves behind a carbocation. And our nucleophile, typically the nucleophile in the case of an SN1 is very often the solvent. It's very often a solvent, so like methanol. This is our nucleophile. Here is our electrophile. The nucleophile simply comes in, traps the carbocation, and you get your product. Plus HBr, we can say. So that's an SN1 reaction. You have an alkyl bromide, in this case T-butyl bromide. The leaving group leaves behind a carbocation, and the nucleophile simply comes in, traps the carbocation, and generates your product. And the rate here is simply this. So the rate law of an SN1 reaction is dependent only on the electrophile. It is not in any way dependent on the nucleophile. And what this indicates is that the strength of the nucleophile does not matter at all in an SN1 reaction. And this rate law that I've just shown you right here should actually seem very much intuitive. This is the rate determining step right here. It is the speed at which the leaving group, in this case bromine, can leave and generate the carbocation intermediate. And as you can see, this has absolutely nothing to do with the nucleophile. It's only a unimolecular rate determining step. It really only depends on the leaving group leaving. And this is why SN1 is called substitution nucleophilic unimolecular. And so this is the rate law. It's dependent only on the electrophile. And so therefore, the strength of the nucleophile does not matter at all like it does in an SN2 reaction. In SN1, nucleophile strength doesn't matter at all. However, the strength of the leaving group, or the ability of the leaving group to leave, does matter a great deal, as you can see in the rate determining step. The rate determining step is really dependent on how quickly the leaving group can leave. And I'll make another video on the subject of what makes a leaving group a good leaving group. We'll do that in a separate video. I think that merits its own video. But just in this video right here, I just want to highlight the fact that the leaving group quality is very much what facilitates a speedy SN1 reaction. So this is a very important consideration. Another one is the solvent. So as I mentioned in the SN2 video, in that case, you want to avoid a polar protic solvent because a polar protic solvent will help to stabilize the nucleophile by hydrogen bonding with it. And of course, in an SN2 reaction, you want a strong nucleophile. You don't want a solvent hydrogen bonding with the nucleophile and stabilizing it because that decreases its reactivity. Well, in this case, it sort of works in the opposite direction. So here, we do want a protic solvent. We do want a protic solvent. And the reason for that is, let's just redraw our first step. The leaving group leaves, and we generate this charge separated species. Now, if you have a polar protic solvent like methanol, then it can hydrogen bond with the leaving group, like so. And as I mentioned, one of the really primary considerations in an SN1 reaction is the quality of the leaving group. And I mentioned I'll make a video on this, but just in brief, the quality of a leaving group, one of the things that impacts how good a leaving group is how stable it is after it leaves. So the more stable it is after it's left, the more stable it is independently, the better it's going to be as a leaving group. And if you have a polar protic solvent, what it means is the solvent is going to further stabilize the leaving group after it's left. So it further contributes to the stabilization of the leaving group. And so this is why a protic solvent that can hydrogen bond with the leaving group after it's left helps to facilitate an SN1 reaction. Now, by far, the most important consideration in an SN1 reaction is carbocation stability. And this is by far the most important consideration. I just wanted to bring up 1 and 2 to conserve some room on the slide, because carbocation stability is definitely the single most important consideration here. And what this amounts to is tertiary electrophiles react far and away better than secondary, much better than primary. And it's the exact opposite order that we see in SN2 reactions. So you might recall in the SN2 video, I said primary alkyl halides react the fastest, followed by secondary, and finally tertiary basically don't react for steric reasons. Well, in this case, it's for carbocation stability reasons. And in this case, the tertiary reacts most quickly, followed by the secondary, and the primary basically don't react in this case. And so to sort of highlight this, let's imagine that we have these 3 compounds. We have T-butyl bromide, we have its cousin, sec-butyl bromide, and we have its other cousin, N-butyl bromide. These are leaving groups, so we imagine that they leave like so. And I'll just show all 3 of them at once. So we have a tertiary, a secondary, and a primary. And in the first case, you're going to get a tertiary carbocation. In the second case, you're going to get a secondary carbocation. And in the third case, you're actually going to get a primary carbocation. And we can actually help to make sense of this with a reaction coordinate diagram like so. And I think this is a really useful thing to look at. So here we have energy, and here we have the reaction. Now let's imagine we have starting materials here. So we have our electrophile and our nucleophile. It's going to rise in energy into a transition state. We're going to get our carbocation intermediate. There's going to be another transition state, and finally we're going to get our products. And this energy level right here, let's say that represents our tertiary carbocation, okay? So that's this guy right here. That's the energy necessary to go from here to here, is this energy right here. And this is the energy level of the tertiary carbocation intermediate. Now, I won't bother crowding this energy diagram by drawing the other 2 coordinates for secondary and primary, but let's just imagine that the secondary one is here, secondary carbocation, and let's say the primary one might be considerably higher. And what this means is that for the primary system, the energy level that needs to be overcome in order to generate the carbocation intermediate is prohibitively large. It is too high of an energy difference to be able to achieve given sort of reasonable reaction conditions. And so basically what this means is primary systems don't react in SN1 reactions. You can get tertiary systems to react, and you can get secondary systems to react in SN1 reactions, but basically primary systems don't work. Now, the other thing to talk about with respect to carbocation stability are systems like this. So we have benzyl bromide and we have allyl bromide, okay? And here are the leaving groups leaving again, just like before, and I'll show them both at once. And the carbocations that you leave behind are these. And you may say, well, these look like primary carbocations. How could that possibly be? Primary carbocations don't work. This shouldn't work. But actually, in this case, these carbocations are resonance stabilized. These are both resonance stabilized. So I'll show the second example. We can show resonance stabilization with this one. And of course, it's going to work the same way with the benzylic cation. You can show the resonance stabilization at 3 different positions in the ring, right? So in this case, we have resonance stabilization. And in this case here, we have inductive stabilization. But what it really adds up to is just carbocation stability. So the stability of the carbocation intermediate is really what determines whether something is going to react in an SN1 reaction. And of course, there are inductive effects stabilizing and there are resonance effects stabilizing. But it all just adds up to carbocation stability. Now, the next thing I want to talk about with SN1 reactions is that you can get rearrangements. And I will actually go through this in greater depth in a separate video. This is the kind of thing that actually requires, I think, a separate video. So we'll talk about both hydride shifts and we will talk about alkyl shifts. Both of these can take place. And so let's consider a very simple example. This, for example. We have this. Let's say we have this. Well, SN1 reaction, the leaving group leaves, right? And what we get is we get this carbocation. Now, interestingly, there is a hydride right here. There's a hydrogen, and the hydride can shift. This is a 1-2 shift. So the hydride shifts from position 2 to position 3. And what you get is you get this. Here's the hydride that is just shifted, and we get this carbocation here. And this carbocation is tertiary, and this carbocation here is secondary. So we have gone, using a hydride shift, we have gone from a secondary carbocation to a more stabilized tertiary carbocation. So in this case, the carbocation has actually found a way to stabilize itself by simply getting a neighboring hydride to shift into its position. And so rearrangements are actually very, very common in SN1 reactions, and it's actually kind of a problem. And it's actually one of the reasons that I think SN2 reactions are generally synthetically a little bit more useful. But there's actually one final reason, and I'll just put it here. And I know this slide is a little bit busy. Hopefully this is all clear. There's one other reason that SN1 reactions are usually a little bit less useful synthetically, and that is because you get racemization. And I'm going to talk about the stereochemical implications of both SN2 and SN1 in greater detail in a separate video. But let's just imagine, let's imagine this molecule here, which is the example that we used above. Let's say we have this. And okay, we have stereochemical information here. We actually have a stereocenter at C2. This is a stereocenter. SN1, of course, this leaves, and what it leaves behind is a carbocation. So any stereochemical information that was present in our starting material is now gone. The stereochemical information that was present in this sec-butyl bromide has now disappeared. And so when the nucleophile comes in to trap this carbocation, 50% traps from above, 50% traps from the bottom, and what you actually get is you get a racemic mixture. Right? So you get 50-50. So an SN1 reaction will racemize. If you have an enantiomerically pure alkyl halide, your product, the substitution product, will be racemic. So that's SN1. And like I said, I know this is kind of a busy slide. I hope this all makes sense. Basically, what's happening here is you have an alkyl halide, you get a carbocation, and the carbocation is trapped. The rate is dependent only on the electrophile. It doesn't really depend on the nucleophile at all. And so the nucleophilicity, the strength of that doesn't matter. The quality of the leaving group matters here, and a polar protic solvent is going to help this process by stabilizing the leaving group even further. And the really principal consideration here is carbocation stability. And tertiary, secondary, and primary carbocations are stabilized by inductive effects. And the tertiary carbocation has the highest amount of inductive stabilization, followed by the secondary and then the primary. And that's the reactivity order here for SN1. So the reactivity order is dependent on how stable the carbocation is. And therefore, anything that can generate a resonance stabilized carbocation can also work very well. And finally, you can get rearrangements in an SN1, and racemization is a thing. And like I said, I'll have separate videos about what makes a leaving group a good leaving group, what makes a nucleophile a good nucleophile. I'll have another video about rearrangements. We'll go into that in greater depth. And finally, I'll make another video on stereochemical implications of SN1 and SN2, and I'll talk about why there's a backside attack in the SN2 mechanism.